so far is we have looked at methods on how to construct control charts. We have looked at phase 1 and phase 2 analysis. We have looked at type 1 and type 2 error, and we have looked into average run length, right? So you have an idea of what these things are, and we can construct control chart and monitor the process. Now the story doesn't end here. Let's consider an example where, let's say there's a manufacturing company in States. I took an example of US Axle Inc. Okay, this is a manufacturing firm that manufactures axle shafts. They manufacture, whoa, this is too thick. They manufacture axle shafts. So to ensure that their axle shafts are of high quality, this company would typically conduct experiments. They would collect data, and data is basically the measurements. And with this data, they will plot control chart, right? They will plot control chart. And once they have constructed their control chart, they can control the process variability, right? They can control process variability. Now, let's say this company has set its standard, but someone is out there to purchase the axles that this company is fabricating, right? Let's take an example of General Motors. Let's say GM is interested in buying the axles that are being fabricated by this company, okay, US Axle Inc. So when GM wants to purchase these axle shafts, GM will have its own standards, right? Purchase axle shafts. They will have their own standards, right? They will say that if the axle shaft do not meet their standard, they would not purchase it from this manufacturer, right? These standards that are set by the customers, customer in this case is General Motors, these standards are called specification limits. Let me write this again. These standards are called specification limits. So let's say General Motors have set the specification limit on the axle diameter. So they want to make sure that the diameter is always below certain upper specification limit and it is greater than certain lower specification limit, right? USL is upper specification limit and LSL is lower specification limit, right? Sometimes they want to put standards on the hardness of the axle shaft, right? So if you're looking at hardness, you don't really want to put an upper limit on the hardness, right? You just want hardness to be as much as possible. So they would set the standard on the lower side, right? They only have lower specification limit on the hardness. There's no upper specification limit. Does it make sense? And similarly, many times you have variables for which you just want upper specification limit. You don't want to specify any lower specification limit. To give you an example, let's say you want to buy drinking water, right? So to ensure the quality of drinking water, you want to make sure that the lead content in the water is below certain value, right? For example, in US, the limit is 15, I think microliters per liter. I'm not very sure, but it's somewhere around this value. So for drinking water, I want to put an upper specification limit, and really there's no lower specification limit for the amount of lead in water, right? It can be as low as 0, right? So this is what it means to say specification limits. So let's put this down a little bit more specifically. We already know what center line is, we already know what upper control limit is, and we already know what lower control limit is. Now, the upper control limit and lower control limit, these values are typically set by collecting data. Okay. We typically collect data, and then from the data, we specify these limits. On the other hand, specification limits, these are set by customers. Okay. Customers in the previous example was General Motors. Remember that. So specification limits are not based on any data or anything. These are based on just some standards that the company or the customers have set. Now, there's one more distinction between specification limit and the control limits. Control limits are constructed by data, so they always track the process. Okay. By looking at control chart, you can tell if the process is in control or out of control, right? So control chart characterizes the process. All right. On the other hand, specification limit characterizes the part itself, the part or the item itself. What I mean by that is, even if a point falls outside the control limit, for example, this one, that part can still be acceptable by the company because this point is inside the specification limit, right? So as long as a point lies inside the specification limit, that is acceptable. So this is acceptable. But if a point falls outside the specification limit, let's say the next point falls outside the specification limit, then this one is not acceptable. Okay, so remember this, if a point falls outside the control limits, all it tells you is that your process is not in control. It doesn't tell you anything about the product or the part. Okay, but if a point falls outside the specification limit, then we know that this point is going to be defective, or this point is not acceptable. So these are the two major differences between specification limit and control limits. Any question on this one? All right, so you might ask a question, why are specification limit outside the control limits? Right, that's a genuine question, right? So it's a good question. And in fact, it is not always likely that the specification limits are outside the control limit. It might so happen that the specification limit and the control limits, they overlap with each other. And it might so also happen that the specification limits are narrower than the control limits. The problem with the later two is that you will have a lot of defective components, right? If I put down the specification limit, let's say here, let me use a different color. So if I put down my specification limit here and here, you can see that the number of defective components will significantly increase, right? And even if I put my control limits exactly as, even if I put my specification limit exactly as the control limit, then also I'm going to produce a lot of defective components. So that's why in a majority of scenario, your specification limits are drawn outside the control limits, right? So just remember that, and we'll talk about this in a moment, why this makes sense. All right, so once the company or the customer has set the specification limits. Now the manufacturer wants to know if the process that the manufacturer is using is it capable of satisfying the specification limits or not. All right. So now the manufacturer in this case is US Axle Inc. They want to know how likely is it for their process to stay within the specification limits. And this is called process capability. So let's repeat this again. Process capability is how likely is it for the process to stay within the specification limits. And to measure this, we have a measure here that's called process capability ratio. And this is denoted as CP. This is equal to upper specification limit minus lower specification limit divided by 6 sigma. All right. And if sigma is not given to you, you can use CP hat, which is USL minus LSL divided by 6 sigma hat, where sigma hat is, you have two different methods of estimating sigma hat. You can use R bar by D2, or you can use S bar by C4, right? So now you can define process capability ratio. Now you can see that we are essentially comparing the width. USL minus LSL is nothing but the width of the specification limit. This is nothing but the width of specification limits divided by our regular 3 sigma control chart, right? We are just comparing the width of the specification limit with the width of 3 sigma control chart. So typically you can have 3 different possibilities for CP, right? CP can be greater than 1, CP can be equal to 1, or CP can be less than 1. When CP is greater than 1, that means your specification limits are outside your control limits, right? Your specification limits are wider than the control limits. That's when CP is greater than 1. If CP is, let me write this down, specification limits are outside control limits. When CP is equal to 1, these two limits overlap with each other, right? And if CP is less than 1, that's when the specification limits are inside the control charts, right? Again, remember, as I told you, if the control charts, if these two control limits overlap with each other, or if the specification limit is inside the control limits, you will produce a lot of defective components. So the later two will produce lots of defective components. And so that's why typically people in this sense is the companies, the manufacturing companies, they would not prefer to have CP equals to 1 or CP less than 1. They will always try to increase the value of CP. They will always want it to be as high as possible. All right, so this is the formula for process capability ratio when you have the upper specification limit and the lower specification limit. But I gave you some examples where you can have just the upper or just the lower specification limit. In this case, we define CPU when you only have upper specification limit as USL minus mu divided by 3 sigma, right? And then when you only have the lower specification limit, you define CPL as mu minus LSL divided by 3 sigma. All right. Now, once you have defined the process capability ratio, you always, as I mentioned, you always want to increase the value of process capability ratio, right? So there are some industry standards, I should say industry standards. And based on these industry standards, there are some values provided for the CP, process capability ratio. So if it's an existing process, if I know how the process works, the CP value, the recommended CP value should be 1.33. If it's a new process, I want to make sure that my specification limits are wider, right? So the value of CP is slightly higher, which is 1.50. If it is for a safety, strength, or critical parameter, and if it is a new process, again, we want to have the specification limits wider, right? So that's how we produce less number of defects, right? So we can write this down here. Increase in CP leads to less number of defects. All right, so I'll stop here. Let me see. Yeah, let's stop here. Yeah, let's stop here.